It really is great to see the room so busy this evening. It's fantastic. Thank you very, very much indeed. Just a few words of welcome and a few points of housekeeping before I hand you over for the real reason that you're here tonight. So the first one is that we are going to record the presentation this evening. I don't know if the speaker actually knows that, but we are going to record. So, and again, that's for all your colleagues who possibly haven't been able to make it tonight but are genuinely interested in the topic. So, always we say, please smile, because not only do we record the speaker, but we take some shots of the audience as well. And if you wouldn't mind, please put your phones on silent. There's nothing worse than somebody's really embarrassing ringtone coming out in the middle of the session. Thank you. We don't envisage there being an emergency this evening, but if there is, the exits are at both ends. Oh, the door is hidden in the corner. I apologise for that. The emergency exits are at either end, and we escape to the front of the building out onto Sheikh Zayed Road. If you need a different kind of an emergency, the toilets, they're located back out opposite the elevators where I'm sure you came up to come to the event this evening. I'm delighted to welcome you. My name is Craig Garrett. I'm the manager of this academy that you're using the space of this evening, and this is really what this space was designed for, is for events like this. So we're delighted that you could use this and take this opportunity to make use of this space. And my colleague Arun, who does the IT magic behind the desk there, also manages the academy with myself. We're based here 100% of our time, and Arun will be the one who will be recording the event as we go. Yeah. Just a little bit about the academy. This is our sort of mission statement: partner with industry as a catalyst for thought leadership and knowledge exchange. Of course, you're the industry that we're engaging with, so it's perfect that you're actually here. And our big thing is knowledge exchange, and that's exactly, again, why you're here tonight. And I think that's why it just fits perfectly with what we're trying to do here. That we have one side of the industry looking to educate the other side of the industry with their knowledge and their experience. So thank you very much for being perfectly aligned with what we are trying to achieve here. We have 7 academies globally. You've seen our spaces that we have here, and they're all available free of charge. And we have a set of standard courses that we deliver. If anyone is interested in any other information to do with the academy this evening, then please feel free to ask us, but that's not why you're here. Just wanted to say a couple of things. The first one is that there is going to be some catering. So please do not leave without helping us eat this catering that's going to come. Otherwise, a very few people are going to have to eat a lot of food. So please remember, don't leave without helping yourselves to the catering. There is also some registration pages are being circulated. So if you've came in late and you haven't seen that, we're just trying to record everyone that's here. We know that some of you have registered online, but we know that there also might be a few people who haven't. Little bit of a plug from my Bentley colleagues who have asked me to mention that, of course, we're here tonight to hear from VSL, and we're delighted that such an industry leader in that field should be here. And they want me to unashamedly plug the RAM Concept Bentley product, because that is something that's used, that is associated with the product. And again, if you want more information on that, please see myself or some of our Bentley colleagues. And it leaves me just to hand over, first of all, not to the speaker for this evening, but first and foremost to the current chairman for the IStructE, Sama. Would you like to come up and introduce tonight's event? Thank you.
You all on behalf of Institute of Structural Engineers. I can see number of new faces which we generally not see. So how many of you know Institute of Structural Engineers are connected already? How many of you already connected with Institute of Structural Engineers? Oh, so many numbers are new, so it's very good. So it's a great opportunity for us to introduce yourself or as an institution to you. So today, first of all, I thank you very much for Mr. Craig to arranging this platform for us to introduce us as an institution, as well as today's topic, which is VSL. So today's topic is Mr. ANNAN. Our speaker is Mr. ANNAN. He is technical director of VSL. Is from Technical University from France. And he is instrumental in developing technologies. What is that? Cable stay technology, correct? I'm new to the cable stay bridges. From lot of people from Middle East, we are very new to cable stay, basically. And he's very active in FIB and PTI. I'm requesting Mr. Anand to take over dais.
Good evening. Thank you very much. Thank you for all of you being there. I'm a bit impressed, so you can pardon me if I eat my words. We're going to talk tonight about stay cables and development of stay cables and stay cable design, making use of stay cable. And of course, you may have a lot of questions. And please, at that time, if you wish, can you ask directly right now the question on the spot so that we can have a bit of interaction into this speech, and this will help me to progress in my speech. I will go shortly as an introduction, presenting the VSL company very quickly in terms of offer, and then of course talk about stay cable. First, in the point of view of components, what is components of stay cable, and then a bit of a word on development, because lately stay cable technology have evolved, pushed by the market, pushed by the needs, the desire of owners, of architects to make it better. So this is what we're going to go through. Few slides. So this is the big WE group company, and VSL is there. A very small company at the bottom, but very innovative. This is why we are here today. A bit of history. VSL has been built as a spin-off from Losinger. So Losinger is a Swiss company, which was known worldwide at that time for construction. And VSL, meaning a Vorspann system Losinger, has been created around a patent of how to anchor wires to an anchor head and transfer this force to a piece of concrete, basically. We call it post-tensioning, eventually. And VSL has been developing the wedge for this 7-wire strand. And from this concept, have developed post-tensioning, stay cable, heavy lifting, and other applications making use of strand and anchor head. Hi, welcome. And this started 1960, and then till now we have developed and broadened our offer to many solutions, application, technologies, and so on. So in few numbers, VSL is around 4,000 people all over the world, and managing patent as any innovative company defending their developments, where we can find VSL on Earth. Basically, VSL works on various technologies, bridge construction, foundation, ground engineering, containment structure, repair. In terms of technology, we're talking about post-tensioning, classical core business, bearings, stay cable, of course, which is the topic of tonight, heavy lifting, and geotechnical. Bridge construction, so this is something we have been aware in here in this region. Bridge construction, we have been quite active there. Foundation, I'll go quickly on all this. Can you talk to me if you need more detail on some of these aspects? Containment structures, and of course, last but not least, repair and retrofit, which is the new challenge of tomorrow, maintaining a huge park of existing structures. And this over past 60 years. Many references in many different fields, and a lot of them is about bridge construction. So let's now enter into the heart of the topic, stay cable. And just a bit again of history about stay cable. First stay cable bridge, 1978, and then since then we have keeping developing, and eventually with various solutions till now. So here we are. In terms of stay cable, we're going to look at it from the point of view of components for the beginning. Stay cable, everyone knows what it is. It's a cable structure transferring force from one point to the other. Today, in the perspective of a new recommendation, a new code, it's seen as a family, 5 families of components. The first one is an tensile element, this strand, which is transferring the load from one point to the other. Second, the anchoring, the anchorage, transferring the force from this one strand to the structure. Yes, please. Just I take opportunity to remind you, if you have any questions, do not hesitate to raise your hand. I'll be happy to answer. So we're talking about strand first. We call it the main tensile element. This name, you can see it in the recommendation. International recommendation, you can see it as well in a design standard and codes like Eurocode, tensile element. And then we have the termination. The termination is a word used in Eurocode. It means the anchorage. It's the component transferring the load from the strand to the structure. Then we have the cable encapsulation, classically the stay pipe, and all the families of components associated to the stay pipe. What is this cable encapsulation? It's the interface between the cable and the environment. It is what the cable sees from the wind, from the dust, from everything coming from outside, including UV and so on. Then we have the protection of the cable at deck level. Quite important. This is where the cable is an interface with the user. This is where the user can touch the cable, can impact on the cable itself. And eventually, we have what we call transition device or deviation device. Is this cable, stay cable, this particularity is it to be exposed to wind, to environment, and therefore it will be subjected to wind forces, wind loading, making deviations, transverse loading, and therefore we have to accommodate this and cater for these deviations. So we have devices. So this is how we're going to structure that speech. If you have any question, please raise your hand again.
Actually, yes. Can you elaborate
Please.
a little bit on the vibration control?
Absolutely. I will do it in a few slides. It's a good question. Oh, sorry. It's okay? This is okay? You have this in mind? So now in terms of application. Today, and especially in the perspective of the FIB code, systems have to be modular, meaning that you can have a technology of strand, the technology of, say, of anchorage, and apply it on various different applications. And this offers some design opportunities. Basically, we have a cable. We have 4 different family of applications. We have stay cable bridge, long span structures, long cables. We have what we call extra dose bridge, where the quantity of live load compared to the permanent load is much smaller, permitting some optimization into the behavior of the structure. Then we have hangers, roof cable, vertical. Then we have, to the other extremity of the application range, what we call bowstring cables or tie downs. And all these different cable application, we can give a bit of classification. I just change the slide. And this classification is made from the point of view of the loading, whether this loading is a high fatigue loading or where there is more deviation or combined. And from this loading, what type of permanent force we accept to have on this cable. Or let's say it differently, what part of the capacity of the cable we accept to have as a permanent force, and what other part is left to cater for safety. So if we go with stay cable, we have high fatigue loading, high deviation potential occurring, and therefore we do not occupy more than 50% of the capacity for the permanent load, basically. If we go with this rose cable, we have a moderate fatigue loading, we have low deviation, and therefore we can go beyond in terms of permanent force. Hangers, these depend on the application. We can have hangers experiencing no fatigue loading and others with high fatigue loading, and therefore this is a decision of design. What is the maximum force you can have in permanent situation? Bowstring cable, usually you have very low fatigue, almost no fatigue, no deviation. Tie-downs, you have low fatigue, but you can have extremely high deviation.
What's the acronym for GUTS? You've got 50% GUTS.
Good question. GUTS means guaranteed ultimate tensile strength. Is basically your cable capacity. Your cable is failing 100% GUTS. 50% GUTS means that you have reached half of the capacity of the cable, basically.
Is this the initial load you put on the cable when you construct, like, or is the final capacity? Look, you can only stress till 50%, like, when you put it, like.
This value usually is the one you have, what we call it, at maximum service state. It's a maximum service load, meaning that if you anticipate to have on your cable a high service load, for your permanent situation, you would stress it initially at 30%, for example. Yeah. So finishing with tie-downs. Tie-downs are cables which are used to restrain a deck of a bridge against the abutment. And most of the bridge, they elongate with temperature variation, and therefore this cable can experience very big rotations. So then you have to judge as a designer what would be the maximum force in this cable in service upon the potential deviation you may have on the tie-downs. So from this classification, VSL, as a stay cable supplier company, is offering a portfolio of solutions. And what is important with these various type of solutions for each application is that they can be combined together. Typically, tensile element, we have various technology of strand. And these have to address the situation of the structure, basically, the exposure to environment, how harsh is the environment or not, the type of loading you expect, and very important, the normative frame in the area, the design codes. Typically, in the USA, is not allowed to have galvanization on the strand on federal projects, and therefore you have codes developed for the use of this type of strand without zinc. For the part of the world, you can use zinc, so it makes the technology a bit different. Why? Sorry. Why in the US we have no zinc?
No, why Americans are not allowing galvanization?
You want which answer on this one? I think it's galvanization is a technology which is extremely polluting. One reason is not all of them, is that galvanization process is highly polluting. Polluting, correct. Polluting. But it's not only this reason. But today, what I know for sure, they are developing a code, a design, or a normative to have zinc into the US as well. But for the moment,
The heat changing the performance of material?
this is true. But it doesn't mean it doesn't work. When you have a material and you apply a zinc process, you change the characteristic. This is true. And therefore, we have different requirements for strand with and without zinc. This is very true. Yeah, correct. and especially if you have silicium in your steel, and then you have a bigger impact on the zinc.
Yeah, you are going to have brittle.
Exactly. Talking about transfer component for transferring the load from the strand to the structure. Same, we can apply various different solutions. Solution with anchor heads, solution with clevises, and solution without any anchor, just by deviation. We introduce the load to the structure through a deviation of the cable. We call it a saddle. The encapsulation of the cable, the stay pipe, has to accommodate the environment, which can be of various form. So it's here to provide to the cable a satisfactory behavior in terms of wind impact. The wind impact is of two nature. The drag first, which is the force that the wind is introducing onto the structure, making it tilting. This is one aspect. The other aspect is dynamic. How the wind is exciting the cable is one aspect of these. Then you can have effect, other effect of the climate. Snow, for example. You can see it later. And of course, the cable is the biggest part of the structure, which is can be seen by users, and therefore it can be a subject to architectural features. Let's call it LED, and then we can see how LED impacts a cable in terms of design, for example. Then we have protection, various types of protection, basic protection, fire protection, blast protection, all of these being required or not, depending on the structure. And eventually we finish with the deviation device, which can be dampers, which can be guiding device, which can be just nothing, just a compacting element to maintain this compact shape of a cable. So we go one by one on all this family. Let's start with the main tensile element and coming back to your questions. Today the standard is this strand, I don't know if it works, which grade is 1860 MPa. This is a new standard which has evolved from the former 1770. Today, the strand industry has developed into a higher grade, 2160. So the industry of wire is increasing the capacity of strand. And today, of course, VSL is proud to have been fully qualified for this application.
Is there any reduction in the extension for failure?
Is there any reduction?
In the extension and failure for the
You mean,
strength?
can I turn your question into, is there any loss in ductility?
No, I didn't ask that. I said
Extension. You mean elastic extension?
Yeah, because that you have got a certain extension upon which you should not allow any further for the ultimate. Yeah?
So the young models is the same.
Relaxation?
No, extension, not relaxation.
So if you apply a higher grade of strand, you can reach a higher extension. This is true. Whether you have a loss in ductility, whether you fail with a higher extension, today there are strand suppliers capable of reaching a very decent extension within the same limit as the extension we observe as a requirement for the 1860. But I don't know if I understand well your question is whether we have a more brittle material or not. Yes. It's not the case, but it's not either the same chemistry on this strand. There is a small jump between 1770 compared to 1860 to 2160. And there is a change in the chemistry of this material, permitting to have similar ductility compared to the 1860.
And this is approved by the international codes?
This strand is a new development.
No, is it
So whether the code is ready to absorb it, to accept it, not everywhere. Not everywhere. So today, the way to approve that use of strand is to make sure that a system exists which can accept it and still comply in terms of performance with the code. So this is what we have done. So we have taken that strand. We have modified the anchoring system to accept that strand. And then we have done testing and passed successfully the level of performance required as for a classical system. stay cable. But if the next question is, can we optimize the structure by this use of strand? The response is technically, yes. Economically, not sure. I explain you why, because the cost per Newton of force is higher with that technology of strand. I told you it's a different compared to that technology of strand. So unless you have a clear technical reason that you need to go more compact, then it might not be optimum, this use of high-grade strand.
How much more expensive? Like 20%, 100%?
No, it's not this. It's not this. We're talking about a few percent. But this depends on if you analyze the global cost in a structure, and if you try to introduce into your cost all other parameters, if for the same quantity of strand you have higher force, you can reduce the number of strand, and maybe you save into labor costs, you save in many other places. But trying to save only on the pure kilogram of material is a waste of time. So this is a strand, we call it PTI strand, which is the strand as it is recommended or in the US, which has no zinc, and therefore has slightly better behavior sometimes, and slightly lower for other aspects. Talking about fretting, for example, is a bit less. Talking about ductility is a bit better, due to the no zinc on the strand. VSL is making use for a specific concept, I'll show later, strand without any sheathing and injection. And eventually, we're talking about epoxy-coated strand. VSL has reference experience with this type of strand, but VSL do not recommend the use of that strand.
Do you have epoxy-coated strands for states as well?
We have experience, but we will never recommend this technology of strand. Maybe we can discuss this. Why we do not recommend this?
Does it crack?
Why? Sorry?
It crack.
Yes,
Well, it's
correct.
It's getting
It
very
cracked,
famous
it-
on internal strands, but then
It
you
seems-
have a lot of wedge loss, etc. Right?
You have a huge setting of wedge, and you have a huge increase in relaxation. Today, we are relying on this strand. Why? Because it has a very low relaxation. And now we introduce technology which is multiplying by more than 2 the relaxation. And on top of this, we have on test, and this strand has low redundancy, meaning that you do not lose one wire, you lose a complete section.
Yeah. It's a localized corrosion.
Exactly.
So you don't recommend just for the stay cables or for post-tension?
VSL position, I would say, is to do the best for the structure. And today we have not seen any advantage of using epoxy-coated strand in any application. Maybe we have overlooked something. Maybe we have missed a point somewhere. But for the moment, we do not see a technical interest in going with that strand for the moment. Talking about anchoring components or elements. So this is basically the standard state-of-the-art technology of anchoring a cable to a structure. 2 types of anchorage. One called dead end, passive end, fixed end, depending on the vocabulary you want to use, and the other called stressing end or live end. Basically, you attach a cable with these 2 anchorage and you stress by the active one. You can stress by the passive one if you wish, but you cannot tune the force with the passive one. You tune the force by the active one. And where ESL has been developing lately is to introduce all these components you have here on the, I don't know if this works, you have here on the, yes, on this part here, we call it the transition zone of the anchorage. For the passive anchorage, they are integrated into the anchor head. The anchor head is a head, this piece of steel, where you have the wedge transferring the force of each strand to the anchor head. So we have all these parts here, which are, which are here in this transition zone, are introduced and consolidated inside this anchor block. This is kept for the active side for one reason, is because from this side you have to stress or tune the force of the cable. So there you don't know where stops the sheathing of the strand. and the sheeting of the strand has to stop inside the anchor block. So we have an extension which is required to make sure that we absorb this position of the sheeting stopping inside the anchor head, and to make sure the system remains tight during service and during installation. You have any question on this? So this anchoring system can be implemented into a structure, and there are a lot of different possibilities to do so. It can, at the bottom, for example, it can go inside a box girder, below a box girder, above the deck through a steel structure. It can be attached to a tower through steel structures, or through the tower, or inside the tower. Everything is modular, and there it's about design possibilities, how to connect it. And
What's the minimum space required for if it is inside the box girder for your jack?
here, for example,
Yeah, the first trick.
here or here, absolutely for the jack. Yes,
But like, is it VSL proprietary jack for the system?
correct.
So what is the minimum space?
So we can tell you it's 1 meter behind the head, for example. But then we can negotiate a bit on this one. For this one, we can work with much more smaller space on the passive side. On the active side, we can as well reduce the space. It's a detailing exercise. We just have to make sure we can do the operation which we are supposed to do, and from there we define what would be the minimum requirement space. It's a good question.
Are you using single strand jacks?
Absolutely, yes.
Sequences become really a headache, yes?
Not necessarily.
How many cables, strands you have got in one cable?
We go from 12 to, or 7 or 3 to 180 something 7. It's a repetitive exercise. It requires a bit of concentration.
And how long would it take to put the forces in one of those big number anchors?
Depending on the stay cable, because you have to thread the strand through, erect the strand, connect the strand, thread the strand.
No, just pulling it.
Just pulling it, it depends on the length.
Jacking.
Jacking it is, jacking itself on its own is 30 seconds.
30 seconds.
But then you have all the process behind, threading the strand through.
No, I was just checking, because you said you have got 170 or 180 strands.
Yes,
So each strand 30 seconds.
yes.
Well, only for stressing.
Only for stressing.
Yeah, I know, that's where
The stressing comes at the end of the installation.
I know, but then that you have followed what's the sequence.
So you have to install the strand from top to bottom and stress it, and then move on to the next strand.
Making sure they are not entangled in between.
So here is an example of application of this type of technology of cable. And you can see cables ranging from, let's say, 50 meter to 400 meter long. So bear in mind, 400 meter long, to erect a strand is a bit of time as well. So when you have a 100 strand unit, 400 meter long, it takes a bit of time. We're talking about 2 days, 2 days and a half. It depends. But then coming back on this system and increasing the force again, then you just multiply the 30 seconds by the number of strands. And you add it up by having something like 15 minutes, 30 minutes, 1 hour, 2 hours.
Just out of question, you eventually have to give the bridge to somebody,
Yes.
and is it going to be a level submission or force submission? You're checking the forces that the bridge should be at a certain level, at a certain time, certain
Correct.
temperature.
This is let's call it a discussion with the designer, what is relevant as parameter. What is very important is that a stay cable is like a structural element. As a designer, we cannot ask a stay cable to be at the same time at that force and that elongation, because they depend between each other based on how the structure behaves. Either you call for the force, you want that exact force, and then consequently you get this elongation as a consequence of how the structure has behaved.
No, I was
with that
talking
force.
about the deck,
The deck, typically.
because the deck should be horizontal at a certain time.
Exactly, the deck should be at a given position. Let's call it the road design line. But then if you ask for a force to be there based on your model as a designer, and this force is such as after stressing the deck is a bit above or a bit below, it's not the consequence of the cable itself, it's the whole structure behaving. And what happens most of the time, especially in composite bridge, is that the stiffness of the deck
can I just say something here?
Yes, please.
Because most of the people here are building designers.
Okay.
And they say, this is up to the contractor to do it. They don't know the bridge designers go through that to come up with all the balancing force, go through the sequences. That's what I want you to say, because most of the people here are building designers. How many bridge designers here? Yeah, so you understand that part, yes?
Thank you. Thank you very much. No, it's true. A deck is a very flexible structure, and the geometry is given a lot by the stay cable themselves, but the support force you have. And tuning the deck geometry goes through tuning the cable lengths. And of course, it's more convenient to call for the force from the designer, give me the force, but then you lose on the geometry. So better to go for a geometry, and then let's check the forces within tolerance and within where we want to be. It's a better way of proceeding. Yeah, correct. We are okay on that part of it. So I just make a. This is a development that VSL started like 15 years ago or 20 years ago. We call it the dehumidified system. We depart completely from the requirement we have today, or the recommendation, which calls for having strand with wax injection, sheeting, a lot of petrol-based material inside. And we replace this passive corrosion protection into an active corrosion protection. How it works is the stay cable system, or the steel main tensile element, including the anchor head, they are in a fully tight encapsulation, and the air inside this encapsulation is dehumidified. The water is removed from that air. This technology is today well spread into protecting corrosion, the deck structure, for example, or box girders in steel. And it works extremely efficiently for cables. Today we have a catenary cable of suspended bridge making use of this similar type of technology for corrosion protection. And VSL has piloted this solution, and today we will try this solution, quite disruptive, which is far away from recommendation, into a project in Hong Kong. Why Hong Kong is because it's very humid and hot, so very aggressive for corrosion, and therefore we have the best field situation for testing the technology. The advantage of this technology is because we have removed all this material, we can make the stay cable much more compact, and we can combine this together with an existing dehumidification plant working for the deck, for example, as a box girder.
So is it a continuous process, dehumidification, or it's like done at some intervals periodically?
If you see that graphic here, this is basically the corrosion rates according to humidity. And what you find out is with a relative humidity of 60% and below, you have almost no corrosion. It picks up quickly very fast afterwards, but below 60%, no corrosion happens. And all dehumidification plants, usually they work at 40%. So the idea basically is to have a closed loop of dehumidification. This is a principle applied in this Hong Kong project, for example. So you keep retreating the same air, and your machine is just here to gather for leakage. So as soon as you have leakage, you have to refeed with dry air, so you dry only the piece of air you add on top in the circuit. And you come at the end of the day, if your system is perfectly tight, the machine works for the first 2 weeks and then finished. If your system has leakage, you keep a little bit. But we are very far, far away from, in terms of consumption, electrical consumption, we are far away from the manufacturing process of the strand itself with the sheeting and the wax and so on. So there you have a global optimization, especially in terms of energy. And today it's quite fashionable to talk about energy saving. So if we move on other technology of stay cable, clevises, I think there is a project in Dubai making use of this type of solution. where VSL has been developing is to have a Clevis stay cable system which has similar type of performance as a heavy-duty stay cable system, not to reduce the capability of the system by having a Clevis. So the testing regime of this solution is similar to the other one, which is FIB and FIB30. So there we have, again, a passive end, the active end, and the force is tuned by threading on this rod into this socket by use of a jacking system. The system is for heavy-duty application. We're talking about a small number of strands, so let's say light stay cable, but in terms of fatigue loading, the objective is to reach the same capacity of the conventional system with this classical 2 million cycle test, 20 megapascals reservation, and so on, and dynamic deviation of the cable. Coming with stressing equipment and, of course, application, mostly on arches. This is where we have most reference for this type of technology, or roof cable, for example. The important is since we are using exactly the same technology of termination with wedge and 7-wire strand sheeted, you can make multiple of it. You can apply, for example, a Clevis together with an anchor head. You can interchange components. It's modular. You can, for example, if I come back here, attach on top a Clevis, and at the bottom having a stressing head like this. Roof application. Now we talk about saddle. Saddle system has been an extremely successful development of VSL. Saddle is the original historical way of connecting a cable to a tower. I'm talking about 100 years from now. And this has disappeared because all the drawbacks of this technology, when we deviate a cable with force and the cable is looking at fatigue loading, you have extremely rapid damage of the cable in the saddle. And so this has disappeared of many recommendations and codes, talking about Germany, for example, or in the US, where in Germany, saddle has been completely banned for a period of time. It comes back to the picture thanks to this type of development where companies like VSL have achieved to develop a saddle which does not compromise the fatigue performance, and which is giving some solution for the classical problems of this technology. How this works? First of all, it works by having an injection inside the cavity. And second, and this is the beauty of the system, we have experience with wedges. Let's apply this wedge concept all along the saddle. So the strand, instead of sitting in front of a round or cavity with only one unique point of reaction, it sits on the cavity which has a shape which is providing 2 points of reaction. And we amplify artificially like this the friction, and hopefully we do it without jeopardizing the interface and without creating fretting corrosion. And of course, we have a main application of saddles is exhaust bridge, and it has been quite successful in Europe. Just one reference I'd like to mention about saddles. This is one application in San Francisco seismic area, and there are designers crazy enough, interested enough to apply saddles in a seismic area, a friction saddle, and how they did it is thanks to this injection of material inside the hole. This material here has a viscosity. So the combination of dry friction plus viscosity permitted to have a nice control of movement during a service type of earthquake in San Francisco.
I suppose you know which cable is going to which hole, and you do it one at a time.
Correct.
Which strand, I mean.
Each strand is parallel. Each strand is stressed one by one, and each strand goes from one anchorage in a defined hole through the saddle in a defined hole
You
to the
probably
other anchorage.
jack them from the bottom to the top, yes.
We jack the strand on two sides.
No, I mean you have got
How you fit in the
a
saddle?
cable, I've got many strands.
Correct.
You start jacking the lowest one first, yes? Or not?
No.
So what will happen if you put, it's going to crush the other ones? Or what?
No. The matrix
You mean in the
it's a
straight
question.
line, it's okay.
This matrix is designed to hold the force of the other strand while the other hole are empty.
So it doesn't matter which order you
Correct. You can leave an empty hole. But it's a very good point to say, because after installation, due to the fact that having installed first the top one and then the one on the bottom, we have to come back and readjust the force on all the strands to absorb some setting of the matrix itself. So it's possible, it holds the force, but you have to reabsorb by restressing a bit the top one at the very end to absorb the vexation that has occurred inside the saddle.
Do you use the same technology for external pulse tension in continuous structures as
No.
mediators?
Talking about, no, not that one. We have different type of technology for this.
Thank you.
Any other question? So this saddle has been used on this Hodayat Stekil project, second Penang in Malaysia, and East Europe, Poland, India, lot of application as well. Here is a nice application where we have been using saddle with a 169 strand, so it's one of the biggest cable we have installed is with saddle actually. This is to say that the size has no impact on the performance. You can upscale this technology with how many strands you want. It's quite modular. Few slides about links. This is an alternative to saddle, where instead of having a continuous cable from one side to the other through a tower, we connect it through a steel structure in the tower. It's a design telling you the size to have a correct behavior between the steel member and the concrete tower. Requires a bit of touchy detail there, but this is an alternative which can work. Some aspect has to be looked at in terms of durability, and especially at the exit part of this link. Talking about link, it's an element which is designed to code and not tested, basically. But then we have to consider the right loading on this link, and of course, if you want to have redundancy in your design, this element, and this is mentioned, for example, into your Eurocode 3111, has to be designed to support the load of the breaking load of the cable, and not necessarily the actual load on the cable. Why? Because if you want to have enough room for ductility, the failure has to happen on the cable and never on this element, which has a very small reserve of ductility due to the size. So these are projects where Link has been installed. Yeah. Some references, mainly in India and some in Europe. Words about transition device, dampers or guides. Guide deviator are usually required to control that your stay cable with the deformation you're going to have during service will not touch the structure, basically. In terms of deviation control, it's not a necessary component for VSL anchorage, but it's very important in case your deviation can go quite far due to whatever effect, service effect, to protect any contact from the cable to the structure. Talking about vibration. Sorry for the sound. Thank you. So vibration, this is these are type of vibration which are meant to be addressed by use of dampers. We call it wind vibration. So this is an example. This is what we call the Meikunishi. The first time we have experienced resonant wind vibration back into the 1980s. Not every cable technology are subjected to this type of vibration. The reason of this high amplitude vibration is because this technology of cable, which is a PWS, they have a very, very small intrinsic damping. So any energy introduced by the wind to the cable is kept there inside. While the strand technology of cable, we have an independent strand. They can have each strand an independent movement, creating internal shocks, internal friction, and this is dissipating energy, and therefore they are not subject to this type of vibration. But still, for long cable, solutions are required. And solutions, they are basically either internal dampers or external dampers. VSL is promoting the use of friction or rubber damper. They have the disadvantage of being nonlinear, so difficult to calculate in terms of performance. Friction is nonlinear and rubber as well. However, these dampers have very good performance, a great performance. There is a technical reason behind, is because they introduce perturbation into the model behavior, and therefore you disseminate the energy in one mode into several modes, which can be directly damped by the cable itself in form of intrinsic damping. And this makes this damper extremely efficient. And they are compact, and a very important point is that a damper is dissipating energy, meaning it transfers mechanical energy into heat to one component, and this component is wearing with time. And no chance a damper contains wearing components that have to be maintained. And the idea of these dampers is to have this component as small as possible and as easy to change as possible, basically.
Does that affect the design life? Or do they have the same design life?
Design life. A damper is meant to control vibration.
Yeah.
The vibration is affecting the design life of a cable. Why? Because it damages components here for corrosion protection. I'm talking about the sheeting, the ceilings, all the specific components that are very sensitive to vibration. So by making use of dampers, you increase the design life of your stay cable. This is one solution to manage the design life of a stay cable. Sorry?
Doesn't it affect the fatigue life?
Yes, except that the strand itself. I mean, if you come back to this slide here, when you look at what type of damages you have on a stay cable because of vibration, it's more or less corrosion protection. Today, we have only very few examples of wire failure due to vibration. There is an example in the US, Sabo Bridge, maybe you know that name, where the cable failed due to vibration, but it's not the wire, it's the connecting part of the cable. A wire that are very strong in terms of vibration loading. But every component you add onto the wire for corrosion protection, these ones that are very vulnerable with vibration. But yes, you're right, Severn Bridge, cable has been replaced, losing wires due to vibration. So
So bridge deck dampers can be installed for different.
shock absorber, you mean? Yes, correct. Here we're talking about dampers for cable. So typically like this, you can see it here. You have the cable here, and the cable is moving. The damper is at the interface between the fixed part of the deck and the cable itself. And it dissipates this relative movement energy through dissipation. It's a different technology compared to the deck damper. Yes. And basically, how you assess the performance of the damper on the cable is by doing a test, and you measure the log deck of the cable. Log deck being how the damper is reducing the vibration per cycle, and you measure how much 2 consecutive cycles has a difference in terms of amplitude, and from there you derive the performance of the damper. So there is a bit of analysis behind to anticipate the performance of it. And this type of analysis, of course, VSL as a damper supplier can support you as designers to define this.
It depends on the frequency of the cable itself.
Yes, absolutely. Absolutely, it depends on the frequency. Here is typically, just to show you this, for the same stay cable is various technology of damper tested. And these are various modes, for example. And as you can see, the frequency can depend upon the mode. And every technology of damper doesn't behave the same way with the frequency. Some dampers will provide performance independent from the frequency, and some others independent from the amplitude. And this depends on the type of function or behavior your dissipative component has. But there we can have a deeper discussion on this, if you wish.
Because usually for DIC we use a tune mass damper. This is a certain mass is connected to the structure through a spring, which is absorbs the kinetic energy.
Correct. This tune mass damper have been tried for stay cable, but the big difference there is that a stay cable can be sensitive to many different modes of vibration, and the tune mass damper you tune it for a specific type of frequency, and therefore you are losing the other performance for the other modes. So what is very important for stay cable is to have a damper which can work with similar efficiency for various different modes of vibration.
I've seen them being tied together. You know, if these are cable going that way, they're tying it that way. Is that efficient as well?
Cross ties, you mean?
Yes.
Yes, cross ties are extremely efficient for damping vibration.
First time I saw it, we started doing it that way.
Yes, extremely efficient, except that it creates a lot of durability issue.
Yeah, you have to keep looking at it.
And installation issue as well. And
Not
when
easy to get there.
Exactly. And cross tie, to manage durability, they have to be tensioned a bit. As you tension your cross ties, you jeopardize the geometry of your stay cable.
Yes.
So whether you want to invest in all these drawbacks just to get the benefit of the vibration control that you can get with this damper is a different question. So basically, the response is yes, cross tie is extremely efficient, but it has a lot of drawbacks. We can provide these cross ties on demand, but this requires a real assessment in terms of design life of the structure, because the drawbacks are significant. For specific application, we can have external dampers, which is basically applying the same concept of dissipative element, but to a structure attached outside of the cable itself. And this is another technology of dampers making use of rubber material. Let's talk about cable free lengths and corrosion protection. Today, most recommendation require to have multiple layer of corrosion protection. And we're talking about two nested barrier, and the interstice between these two barriers is filled with a hydrophobic medium. So this is a typical FIB concept, where the two barriers are here the PE coating, here the zinc, and in between you have this wax or this grease, whatever, hydrophobic medium. VSL is promoting as well, as we said, the active system for corrosion protection, which is making use of dry air, where we have an external barrier, which is a stay pipe itself, because it's tight. We have a zinc inside it, and in between you have a dry air, which is a hydrophobic medium as well. But this raises up the question of the durability of this stay pipe. If it's part of the corrosion protection concept, therefore it has to be, the performance of the stay pipe has to be assessed in terms of durability. This component is plastic, HDPE. We know plastic are degrading with UV and light, and therefore there are tests to be performed to qualify this. And just to keep in mind that many colors are available. Not all these colors survive the same type of solar exposure. We have a much higher, better performance for the white, gray, black compared to the red. a red stay pipe in Dubai will not stay red for a long time. This has to be kept in mind of designers to make sure that the right color is chosen. A stay pipe primary function is to protect the stay cable, and secondly, to make the stay cable having satisfactory dynamic behavior according to wind. And again, what it means have a lower drag coefficient and making the stay cable insensitive to this galloping phenomena or vibration phenomena. So this has to be assessed through wind tunnel testing, and this type of test has occurred regularly to assess this performance. Today we are making use of RIP technology to achieve this, but there is various technology of RIPs. Another issue which is picking up lately is the ice is not hopefully an issue here in Dubai, but on some countries it's extremely dramatic as an issue. Ice is today accreting on stay pipe during a cold period, and when the temperature is rating up again, it falls in big pieces and really introduces severe damages. And this is the latest big track field of development. First, to understand how this ice accrete on the stay cable, and second, what solution can be implemented to avoid this ice to fall down. It's just an example of requiring university research, and we have PhD ongoing on this matter, exactly on this matter.
Heat it up.
Sorry?
Heat it up.
Make a big radiator. Global warming, you know about it? Exactly. So these are solutions we have been developing. Heating is one of these. We have others, and this is what we investigate today. We are very proud to achieve the lab test on one solution which has been proven in lab actually to be working extremely well. We can go in detail on this one day. LEDs. This concept picked up here in Dubai a long time ago for a project which is not yet here. It's, from the engineering point of view, a very nice challenge. Aesthetically, it's questionable. I think it's a matter of architects. But in terms of design, it's a fantastic challenge. Introducing a light onto a stay pipe and expecting this light to be in the same position after 5 years and shooting on the same direction, because this is what is part of the architectural design, is a challenge. And we are very happy to have taken this challenge and find a solution for this, addressing either the installation, the replacement of the LED, and of course ensuring an LED positioning all along the lifespan of the stay cable.
Sure, yeah.
So we have had the first mock-up here in Dubai for a couple of times. A few words about cable protection. We're talking about protecting these areas here where users can access. Defining a protection for the stay cable goes through a risk assessment. It depends upon the design first, whether this design has enough redundancy to accept damage on the stay cable, and upon some risk related to the use of the structure. And to help designer or owner to make this risk assessment, we have developed this different protection level rating, where P0 basically is when you have no protection, only for environmental impacts, rain, wind, dust, and so on. P1 is what you're going to find on most of the bridge, is unintentional effect of a user on the cable, anti-vandalism, environmental impact. P2 is typically for a bridge which is missing a bit in terms of design of redundancy, and therefore we have to make sure that an accident happening there will not jeopardize the bridge itself, or in a place on a structure which is a bit strategic in a sense that it cannot afford to be closed for a period of time for replacement or repair. And P3 is for strategic infrastructure located in a geopolitically unstable area, like the US, for example. Sorry. So these are, yes, heavy protection, blast protection, and so on. Talking about fire protection, this type of event can happen. So we have many examples of events where a truck can catch fire. We're talking about a hydrocarbon fire, 1,100 degree. The duration of the fire depends upon the situation of the structure, whether it's far away or close to a firefighter facility and so on. And from there, we develop fire protection. These fire protection, they are here to provide to the cable itself, the main tensile element, sufficiently low temperature so that it can hold the force. And this is assessed by tests. Tests today, they are mandatory according to PTI. They are coming onto the picture in FIB again. And there are various types of rating of fire protection, mostly depending on the time, the duration of fire. The temperature of fire itself is 1,100 degrees, basically.
One of the load cases, the design cable state rigid, is for the case that one stay is not there, isn't it?
Correct.
So
we call it redundancy.
the bridge should stand even if it loses one cable.
Yes, correct. Today, at least if we follow Eurocode as a design document, we should have redundancy of one cable.
Yes.
And some of the code is even more, and some is less. But then, from there, we take a decision on whether the design has already accommodated for a fire risk or not, and if not, we can reduce the consequence of that risk by having a protection. It's a risk assessment approach, which involves design and component itself, basically. So this is an example of a bridge making use of fire protection and blast protection. One slide about blast protection. Ultimately, VSL is developing one solution, capitalizing on the fact that as part of design, a stay cable is under permanent situation, is stressed to 50% of GOTS, meaning 50% of the cable capacity is redundant, is there just for safety. And the idea of this concept is to make use of this 50% additional strands to protect the core one inside in case of blast, basically. And how we do this? By having an individual protection for each strand, and the outer strand are deflecting whatever load, blast load, and provide protection for the core one inside, making the blast protection extremely compact and lighter a bit. So now we have been through almost all these components. If you have any questions, don't hesitate. Shall I go on stay cable development? R&D, I had a feedback earlier today about stay cable technology as having evolved extremely quickly lately. Stay cable is still a domain of steel engineering where there is a lot of development today. And the R&D can be made either in-house, as VSL is doing, and as well with universities in partnership with a designer as well. And latest development are this LED and ICE issue. We have not been talking about this. Installing stay cable, same as mentioning, it's technical work and requires a bit of training. And today, this training is not systematically given into universities. It's the role of each specialist contractor to train their staff into installing stay cable. The performance of a stay cable, and this is something quite important, does not only depend upon the quality of its components. It depends as well on how on-site this component has been assembled and installed. And VSL has developed an academy where there is a mock-up where these installation methods and tools and equipment can be commissioned, where staff can be trained before going to a site where they have to perform for the very first time.
So VSL can train the staff for other companies?
It's a good question. The response is yes. We are willing to offer this. For a contractual scheme where the cable is installed by another party, yes, the intention is to offer that these workers are trained into our academy for our components. Yes.
What will happen to guarantees if somebody else installs it?
This is a very classical contractual discussion. And this is why it's very important to have the labor installing the stay cable or the post-tensioning system trained into our facility. And for sure, this is going to solve many issues.
To anybody else, you will install it.
Yes, it's a good point from my colleague. In every situation, we are supervising the installation on site, always. Stay cable testing and development qualification. Today, I'm going a bit fast here, but I'll come back afterwards. There is no such thing as approval for stay cable. And there is a reason behind. It's a very fast evolving market. The technology is changing quite rapidly. And therefore, there is no international body capable of locking today an approval type of qualification. And therefore, we are working with recommendation documents. And these recommendations are for designers, for you to ask the right questions to people like us in terms of performance for a stay cable system. Today, the two documents which are used worldwide are the PTI, mainly coming from the US, and the FIB coming from Europe. And they are providing guidance on what type of testing should be required for what type of application. And these documents are the base for us as a stay cable supplier to achieve our design by the right qualification testing. So today we have likely a new release of the PTI last year, and as well a new release of the FIB last year, which is an achievement from a long whole work from the FIB committee. We have as well now another document is a code. It's a Euro code, and the Euro code is in process of being reviewed as well. And the next new thing that's going to occur on this Euro code now is that the appendix related to testing will become normative. Meaning today is just an informative appendix on the Euro code for testing is becoming soon normative. It means that it's a must to have this system tested. So what type of test are we talking about? We're talking about a fatigue test, where we are aiming to confirm the actual fatigue performance and the bending fatigue performance. This is newcomers into the FIB 89. And this is to address ULS situation, ULS design situation. For SLS situation, we have a test to qualify the serviceability of the system, which is a litmus test. We make sure that the system is offering a suitable service performance and for solid friction test. But it's not everything. We have as well qualification of stay pipe or encapsulation, which go through wind tunnel testing of two types, drag coefficient and dynamic behavior. And basically, we have as well, on top of this, tests for the deviation device, dampers. These tests are mainly done on field, and they are here to prove our assumptions on damper requirement and design. A few words about installation, quickly. Stay cable, the way they are developed and promoted in this company is strand-by-strand systems, which are stressed strand by strand, and maybe you can come back to your question about smooth installation. And basically, it consists into erecting first a stay pipe with one strand inside, and from this stay pipe in place, threading one by one each other those strand, and stressing them using an equipment. Hopefully, this equipment is a bit modern by having automatic record of information and so on for a more smoother relationship with the designer in terms of exchange of information.
Was there anything to do with rain as well?
You're talking about the stay pipe? Yes, correct. These ribs, they are here to cater for a phenomena of vibration. We call it rain and wind. But not only, and especially lately, based upon the last PhDs performed in France on the CSCB, they found out that the biggest positive impact of the rib is for the dry galloping. And the theory of the rain and wind can be questioned again, whether we're talking about surface texture or whether we're talking really about a rain rivulet. Yes, correct. But this can be summarized into dynamic behavior. So this is why I call it dynamic behavior with the wind, or wind interaction, dynamic interaction with the wind. Yes, it's a good point. So here, installation of stay cable with saddles. With saddles, two cables are installed simultaneously, the one on the left and the one on the right, because the strand itself, the maintenance element, is going through the tower. It's one piece of strand, anchored one anchorage to the other, going through the tower. And of course, this is the type of equipment you have on site for installation. The important point is that it's not heavy equipment, and this is why this technology of indoor strand cable has picked up in front of other technologies like PWS. It's because we are manipulating low-weight equipment and components. We're not here to manipulate a 25 tons cable. We're just manipulating a coil of 2 tons. And with this one, eventually, we're going to make almost 100 tons stay cable. Last but not least, monitoring, maintenance, repair, what happens during the service life of a stay cable and a stay cable bridge. Monitoring is quite fashionable. We have to manage the service life of a structure. A stay cable is a very good prop to understand the behavior of a stay cable bridge. Knowing the force of a stay cable gives you a lot of information on the bridge itself. And these structures are highly exposed to environment, and therefore they require a bit of monitoring. So we're talking about on-site measurements, data manipulation, treatment, and interpretation analysis. So all this process has to be implemented. Maintenance of stay cable system. Today, one information about new technology, and especially this one from VSL, is that they are designed to be maintenance-free. This is opposite to a locked coil system, which requires, by design, a regular maintenance. This type of cable requires no maintenance for 100 years, let's say. However, this information, this design is based upon information we have today. And a big part of what happens on stay cable is unpredictable or unpredicted, and therefore inspection is required and is a must. And another way of saying things is that a maintenance program is established for stay cable based upon finding from inspection. And from finding from inspection, you understand what would be particular lifespan of particular components of the stay cable, and therefore you can tune your design plan. So when approaching a project with stay cable system, according to this state-of-the-art technology, we have to bear in mind that the final maintenance plan is developed along the service life of the cable itself, based upon finding from inspections.
How can the top portion of the cable be visually inspected at this higher level?
On this bridge, for example, we have an access.
About the periodic inspection.
Yes. You have two locations in your stake cable where you can have effects, where you can tune and understand how it behaves with age. It's near the anchorage. This is either here or here on top. So you have an easy access here in this anchorage.
This is reachable. What about the top?
In the tower, you can reach the anchorage which is inside the tower. Usually these towers are built with a void inside, with a core inside, you climb up, and from there you access to the anchorage. And then, if you want to have an idea of what happens outside of the tower to the cable, either, and this happens, we go with climbers, or you check what happened at the bottom there, which is more loaded. And if you find out that you have no issue here at this location, you can deduct that maybe there is not much issue on top as well. The risk that you have an issue on top is lower. If now you start to have recurrent issues at this location, maybe you want to invest into having a more deeper investigation of what happened on the top. So you can adjust your inspection program according to your findings.
Usually this tower is reachable at the top point of the tower?
From the inside?
Yeah.
Yes.
It depends on the tower design.
It depends on tower design. Yeah, correct.
Is there any approach to monitor this detail using cameras or whatever?
There is with some of the modern repair and monitoring things where drone technology and things is now improving to an extent that you can get much better access using drones to fly up and do camera inspection externally. That's developing with time and improvement of the current technology, so which is a lot easier than, as Rashid said, the older method, which was you sent climbers up.
Because I feel this point is not always reachable. Sometimes this tower is solid, not.
Yes,
not
correct. If you have a saddle, for example, if you have a saddle, the tower is solid. So you have some design where there is already some lifting device attached to the tower. I'm having in mind, for example, Wadi Leban in Saudi, where you have a lift directly there attached to the tower for inspection, for future inspection. And you have projects where nothing has been considered. And then, of course, when you arrive on the spot on this project, where nothing has been considered, you have to establish or to organize an access on top, which can be difficult or easy depending on the situation. Yeah. It's a good point. It's a good point in the sense that at phase of design, access for inspection, sometimes they are forgotten and they are very important. And a design permitting inspection and providing access, it's a lot of headache glass for the future. Yeah. So force monitoring or other type of monitoring can happen. We have two technologies for force monitoring, load cells. We have as well two different type of load cells, magnetic load cells, resistance load cell, and we have behavior assessment, let's call it vibration assessment methods for force monitoring, which can be extremely accurate, As for information, a small story, Queen's Ferry Crossing, one of the biggest take-killer projects in Europe. The designer has considered the vibration assessment of force as the most reliable one for his project, and has finally tuned the bridge according to information received from vibration force measurement. Repair and retrofit, very important. This is a type of incident that can occur on the stake cable. Here's an example taken from Qingchao Mingyang in China, where a barge basically, after a storm, detached from the harbor and hit the stake cable bridge. And it hit it by the crane through the cable themselves, which was a very nice and interesting exercise of how to test stake cable replacement by occupying the smallest part of the bridge deck. And it was a nice training for VSL. behavior of the whole structure. Here, VSL kind of offer capabilities in health monitoring, assessment of health of the structure based upon measurement of data from sensors. And here we go as a conclusion about inspection. Few references, maybe. This is the end of my speech. Sorry for having been so long. Just a few bridge pictures. Queen's Ferry Crossing, Mersey Gateway, saddle project. So these are stay cable with saddles. Hangars, roof stadium, extra-lows bridge, various type, mainly using saddles. Stay cable bridge, making use of saddles, and link, possibly, which bring us to this conclusion. About stay cable, what is important is it's one of the most dynamic field in civil engineering where we still have development, very interesting development where we have still PhD university running on. It's an interesting topic. What has made VSL being a leader in that matter is by performing the R&D themselves and by proposing and offering a range of components, modular, and a wide portfolio of different solutions for various applications. And voila. So this is it. Sorry again. The wind coming from down?
Yeah. When everything went on the bridge down, how can this cable?
The deck is responding to the wind coming from.
When coming down the bridge.
Yes. So from the point of view of the stay cable supplier.
What usually coming can be one coming more and this cable.
Yes. So what we call it a parametric station is when the wind or the traffic is affecting the deck behavior, and this is exciting the stay cable itself.
Yeah, his question is how the tension, if the bridge deck is very lightweight,
Yes.
the wind is more, there cannot be tension. So your bridge deck is high weight, basically.
Yeah, the static part of the wind force is marginal. What is important is how dynamically this deck is behaving exposed to that wind. And maybe the deck is vibrating because of the wind. And maybe this movement of the deck is introducing vibration to the stay cable. And this starts to be quite critical because this is one of the most severe cause of vibration on cable, what we call parametric, is when the vibration of the cable is induced by a movement of the deck itself. And this happens when the cable frequency, the mode of the cable are close to the one of the structure itself, especially the deck. But the static force of the wind itself is not significant in terms of loading compared to the other loading you have on the structure.
How much initial pretensioning requirements? I mean, you have to pre-stress first, and remaining reserved for the axials and live loads. So initial pretensioning, how much you recommend for that?
It's a good question. Today, we wish not to force designer to have an initial pretension, meaning that if we are facing a stay cable where the pretension is very low, ourselves as a stay cable installer will artificially organize a interface between the wedge, the strand, and the anchor in a way that this has no impact on the performance. So to make things easy, if you have 30% of guards as tension, it's perfect. It's quite fast, quite easy to manipulate. If you go much below, if you have only 10%, 5%, if you have 10% or 20%, we're going to apply what we call power seeding. We're going to power seed the wedge to avoid any issue linked to the fact the tension is low. If you go even below this, talking about a few 1 ton per strand, or even less, then we'll power lock the wedge. That means we're going to lock the wedge to a higher force to make sure that nothing can happen, even though you lose tension into the cable itself. So depending on the situation, we adapt ourselves, our method of implementing the force on the cable to make sure that we have a satisfactory mechanical performance, even though the tension is very low. But bear in mind, these cables, they are working very well with high tension. This is why cables are good. They like high tension. High tension means good behavior. So do not hesitate to optimize your cable cross-section to maintain the tension percent at a sufficient level. Unless you have a service requirement or flexibility, otherwise let's go optimum.
In one of your slides, you mentioned guts, like guaranteed ultimate tensile stress.
Yes.
In the range of 50%.
Yes.
Why it's so low? Is it generally in building industry go up to 75% maximum?
It's a good question. Usually on post tensioning, we go to 70–80%.
75% generally in building industry.
Yes, correct.
Yeah,
this is correct
why is low here?
on post tensioning. Because in buildings, because the post tensioning system in buildings has no fatigue loading, almost zero fatigue loading, and no deviation. You put the cable at the position, you pour the concrete on your slab. Then when the concrete is cured, you introduce the tension, and then the force will be the same, and the ductility will be the same, and then it's finished. This cable, we have the force changing with time, and this will reduce fatigue. And therefore, we need to have some reserve of capacity to cater for this fatigue loading. And this is the reason why we reduce the tension. So maybe it's too pessimistic here or too conservative approach, the 50%, and this is today under discussion to this recommendation document. But this is one reason. There is another reason, is relaxation. One of the aim in using the strand is to have no relaxation. The strand is a very good product, the 7-wire strand, because it has very limited relaxation. But we guarantee this very, very small relaxation when the force is not that high. And 50% guarantees you that you don't need to bother with relaxation at all. On the cable itself, not on the structure, but just at least on the cable itself.
I remember there was an equation called Ernst equation.
Yeah.
For the actual stiffness of the cable.
E equals to
yeah, because the cable length and other things changes it.
I think this equation is related to the sag of the cable.
Yes, correct.
Let's call it the second order
effects. Yeah.
You
have to allow for that.
Yes, this is correct.
We don't think it is PA over L. The stiffness.
Yes, correct. But this is depends upon the geometry. So if you do the calculation with the software, make sure that your software has a secondary order calculation modules inside, and then you can just ignore the Ernst equation.
Software was hand calculation.
Yeah. If you have your hand to calculate, just don't remember. Don't forget the equation. It's true.
Yeah. One question. During construction, you stress a state, then another one, and then your previous states obviously undertake more force.
Yep.
So during construction, how much do you recommend to not exceed of the guts?
This information is provided into a FIB document. There are information about it. Usually what is applied is
even if under permanent you go like 50, during construction you can go to 85 if required, right up, or 80, or as long as you control the elongation, etc.
In the FIB, the value of 60% is mentioned as a maximum during construction. But I don't think you would go much higher because during construction, all the superimposed dead load are not there. You do not have all the parapet and so on, and you don't have the maximum live load. 50% guards is the maximum service, meaning that under permanent situation, you would have maximum 40. And during construction, usually, it's recommended not to exceed 60%. While we know for individual strands, and especially the first one, sometimes we can go up to 70. But this is allowed, assuming the force is not there for a long time.
Yeah, it's temporary.
And only 1 or 2 strands, not more. Yes, correct.
But can this allowance be used in the extreme cases, like during your construction, you happen to happen an earthquake? So your forces, like you have like 10 stays in the design, but you are only 4 actuators. But then this stage is gonna take much more higher forces. Like in those cases, can you go up to 70 or 80? Like, do you have any testing done for it, or do you have any research done for it?
But what you know is we do a tensile test.
Yeah,
for sure.
That's for.
And tensile test, you have to prove 95, 98% of GOTS. And 92% of IUTS, which is the actual force on your capacity on your cable, 95 of GOTS. And this, we know the cable can handle this. So it's just a redundancy, it's just a safety. Whether you're gonna fail with your cable because of a stressing at 60, 70, I'm not sure, but you have to respect sufficient safety rule. But we can always discuss on this detail, how much force you want to have per strand or in the cable during construction.
And last question.
Last question. I had seen 2000 catalog for 2000, this strain system. At that time, you were allowing 45%. So in 20 years, you have done good technology research. So we have jumped from 45 to 50%, which will help structure engineer. In that catalog, we had a stress variation around 200 MPa under full tension and less tension. So now, how much we can allow the stress variation in a strain?
You say making use of which strand? The 1860 or the
1860.
1860. It's a good question. I try to find the good answer for you.
Yeah, like because I remember, I was fortunate to work on Mumbai-Pune, this Mumbai extra-dose bridge, the cable-supported bridge, which had a span of 250 meters, designed by HNTB. At that time, we were using 200 MPa stress variation and 45%.
Yep.
It was sometime 0.42.
2000, yeah, 0.42.
Not 0.45.
0.4.
0.42 is coming from the German DIN standard.
Yeah, but I'm just saying 0.42 we were looking at.
So today, the FIB says you can have 50% maximum service. And to make use of this 50% maximum service, that means that the stay cable has undergone a test at 45% and 200 MPa tuning cycle. 200 MPa and tuning cycle, yes, correct. This is for stay cable application. If you go extra dose, you can go higher than 50%, you can go to 60% maximum service, meaning that the system has undergone a test at 55 maximum, 140 MPa 2 million cycles. But this is the equivalent, what we call the characteristic fatigue loading. What you have to do as a designer is to estimate the characteristic stress variation based upon the Eurobridge response, which is not an easy exercise. We call it the Pangan minor summation of damages, where you compute this equivalent stress variation. But today the limit is 200. Then if I go a step beyond your question is what happened with higher stress variation. So we have made one test one day in VSL, and we have made a test with 250 MPa stress variation, 10 million cycles, and we passed it. So whether this 200 MPa 2 cycles is a limit, the response is no. It's not a
psychological limit.
It's just a position where designers believe they have enough room for design. And if they feel they don't have enough room, we can go beyond, but then we have to qualify this. But we have had a test with 10 million cycles, 250 MPa on the strand system, 619 in Vienna. Positive test. True. And now there is one question about this super high grade strand. So if you seek as a designer for optimization because you make use of this 2160 MPa grade strand, you have an optimum for your ULS verification. You are happy. What happens with the fatigue? If you reduce the cross section, what's going to happen with the stress variation at the end? So of course we have to apply a different rule. If we today with the 1860 we have 200, and you seek for optimization by making use of 2160, maybe you would like to have 250 MPa stress variation, and then you can have an equivalent optimization.
Just imagine you have a problem with your PI, you cannot get it anywhere. So that's where we stop.
Yeah, thanks.
Thank you. Thank you, Mr. Kanan. It's a great presentation for all of us. As majority of us are from building industry, it's interesting for me, particularly durability aspects of the cable. So we're looking forward to see a project in future, which is if it is anything is happening going to be in here. And thank you very much again. And thank you to VSL for arranging a dinner also today. And again, thank you very much for Bentley Systems for arranging a nice venue.
Thank you, thank you. Just two quick things before you go. Would you believe this room was cold earlier and we were worried? Now with 100 people in it, I think we're feeling the heat, so we need to be moving. And there was 2 registration sheets that were being circled earlier. Could somebody sort of say where they are? Oh, there's a book. There was also like a kind of clipboard. Oh, they're up there. Perfect. Thank you. There was so many people who all arrived later, and we need to make sure that we catch up. We're really interested to catch everybody who's attended tonight. So if you did arrive late, please, or you haven't had a chance to sign into one of those books or sheets, if you could just make sure you do that before you leave, that would be really appreciated. There is a massive amount of food now in the room just behind us. Please make sure that before you leave, you enjoy some of the catering. That again has been provided very kindly by VSL. Thank you very much. Thank you.
Thank you.